relation. In this form, in the present form, which I described before, it can be applied to the ground states. However, extension of the method to excited states is possible. I will speak about that later. And one of the advantages of the methodology is that it can be used with any approximate density functional, right? And it has a relatively low computational cost, mean field cost, maybe factor of 2 slower than the usual DFT calculation. But on the upside, it can describe the strong non-dynamic correlation, which the standard Kohn-Sham DFT cannot. I will briefly describe some applications of the method. So I skip a few slides, and I will show this slide again, where you see that for the equilibrium geometries of some molecules, such as hydrogen molecule, H2, or ethylene molecule, planar ethylene molecule, REKS method yields exactly the same total energy as the standard Kohn-Sham calculation. However, REKS allows us to describe bond dissociation, either sigma bond in H2 or pi bond in ethylene molecule correctly. This is a big advantage. And how do I know that, for example, that the description of the non-dynamic correlation, so in this region or in that region, is accurate enough? So I can show you one example which demonstrates the accuracy of the method. So tetramethyl ethane diradical is one of the molecules that has been studied previously quite some time ago, almost 50 years ago. First, it was detected. This is biradical because there is no closed shell Lewis structure you can draw for the ground state of this molecule. And some experiments indicated that it may have either triplet or singlet ground state. And we did REKS calculation for this molecule for potential, you see potential energy curves for the singlet state, which is blue, and for the triplet state, which is red. For triplet state, we used the just usual spin restricted open shell Kohn-Sham. And these curves are shown along the bond twisting coordinate, this angle, twisting angle, twisting around the center of CC bond. And as you see, the two states, they even cross at the REKS level. But this result, which we obtained back in 1999, was very soon challenged by, say, people who used to do SCF CAS-PT2 calculations. They quickly did their calculations for the same molecule and obtained these curves. So they never crossed. They claimed, well, CAS-PT2, you know, everybody believes that this is the golden standard in the multi-configurational quantum chemistry. And for a while, this was just hanging question, which one is correct? Until some time ago.
Which one is which? I don't know which one is which.
Yes. You mean?
The solid line is a REKS or CAS-PT2?
Solid line is REKS.
Okay, okay.
Solid line is REKS. So this REKS singlet state, blue, and red triplet state. And now you see dashed lines. This is CAS-PT2 triplet, CAS-PT2 singlet. So as you see, they don't, I mean, triplet and singlet don't cross anywhere. So this was a kind of challenge, and it was kind of resolved with quantum Monte Carlo calculations, which were carried out in 2013 and then 2014. And this was, I think, diffusion Monte Carlo. And they obtained these energies shown here with these asterisks, blue asterisks for the singlet state and red asterisks for the triplet state. So as you see that REKS predictions, which were made like 15 years before quantum Monte Carlo, they are essentially correct, but CAS-PT2 was wrong in comparison with quantum Monte Carlo. I will not show many more, say, examples of applications of REKS. I will briefly mention only that REKS methodology, which was before described only for active spaces with 2 electrons and 2 orbitals, can be extended further to active spaces of larger size. for example, including 4 orbitals and 4 electrons, or even 6 orbitals, 6 electrons, and so on. Only we need to make sure that we have proper number of variational parameters in the formulation of REKS energy functional, and this is enabled by the use of generalized valence bond ansatz, generalized valence bond wave function at the near 0 or 0 electron-electron coupling strengths to construct the energy functional for the REKS method. So, for example, the use of GVB leads to a very simple energy functional for the ground state of a system with 4 active electrons in 4 active orbitals. So, and here you see the configurations involved in the in this energy expression, and deltas are essentially the coupling, exchange integrals between the respective orbitals. But in GVB, we split all the orbitals into some sort of coupled pairs, where we introduce simple wave functions of this type. So double excitation. So one of the wave functions, one of the components is double excitation from the other, like here or here. And that enables us to write the energy of the wave function and the energy of the ground electronic state in a very simple form, which has exactly the required number of variational parameters. In this case, 4. So 4 orbital occupations, fractional occupation numbers of orbitals A, B, C, and D. No more than that, because CAS SCF wave function or full CI would have many more variational parameters, which would be incompatible with the idea of ensemble DFT. So this method is implemented only in TerraChem program designed and developed by Todd Martinez group. And for example, it enables proper dissociation of hydrogen chain. Here you see chain of 4 hydrogen atoms, and as function of distance between atoms, the energy goes to proper dissociation limit. However, to be able to describe some other molecules, such as double bonds, some extra terms need to be included into this energy, added to this energy expression, which I will describe later on when describing methodology for the excited states. So I will summarize now that REKS method for the ground states provides accurate symmetry adapted description of strongly correlated electronic states, such as states of biradicals, molecules with broken bonds, magnetic coupling. So avoids problems with spin contamination and can be used in connection with any density functional. So it has very low computational cost. And current implementations include REKS with 2 electrons in 2 active orbitals and REKS with 4 electrons in 4 orbitals. However, further extensions of the methodology are possible, and I hope they will be developed in the future and implemented. So now let me to switch to the part 2 of my lecture. So excited states.
Michael?
Yeah.
Can I ask one question?
Yes, sure.
What do you think the practical limit of the maximum size of active space for the REKS? Because I guess if the CAS space is larger and larger, then the configuration, the number of configuration increase exponentially. So
not exponentially, it will increase only because to construct these energy functionals, I use GVB, and it leads not to exponential but to polynomial increase. And furthermore, it's even maybe even milder.
I think it's a linear.
Yeah, it's linear, basically linear in the number of GVB pairs. So each GVB pair is described by, some call it geminal, this wave function, simple wave function. And in general, the total wave function is represented as an anti-symmetrized, so this is anti-symmetrizer product of these geminals. Right, so I need to split all orbitals into respective orbital pairs. There I can use chemical intuition. For example, if I have pi and pi star orbitals, it's natural to include them into one geminal. So that will be pi, pi star, sigma, sigma star. Quite often.
Yeah, I guess the confusion is coming from the differences between this and the constant CF. Well, constant CF is a coefficient,
Right?
The configuration coefficient. Here, occupation. So occupation reduces dramatically the number of possible configuration. You only use this few. So it's a number of configuration. It's just a number of occupation.
Right.
So it's a linear. It's not even yeah.
Yeah, exactly.
But
yeah.
More proper question for this would be then, because of you have a more and more configuration, you have a more folk. You need to build more and more folk matrices. That would take more time. But my question would be that. I checked recently UHF, but then I found that we form alpha and beta folk at the same time. You calculate, you just do the integral once, and you form all folk at the same time. I think that you can do the same thing here.
Absolutely, that's my idea, and I think that in some programs it is already implemented, especially in the programs which are designed to include translational symmetry and do calculations with periodic boundary conditions. Because when you sample across the, say, Brillouin zone, you need to perform a computation of multiple Fock matrices at different sampling points. And this can be quite large number. It can be 30, 60 sampling points across the Brillouin zone. And to speed up the computation, this trick already is being used in many programs. I'm pretty sure that it is used in Crystal, although I have never seen the code of Crystal. I know that it is available in Gaussian because they can build in parallel the required number of Fock matrices, provided that they are given the appropriate number of density matrices.
Yeah. So then I mean, the integral is the most time-consuming part.
Right. Yeah. Exactly.
Once you have a Fock, the rest is just a linear algebra, which is not a really bottleneck here. So yeah. So
right.
It doesn't really I mean, that much increase of computation cost, right?
Right. Indeed, always computation of the Fock matrices can be done in parallel. And then
I mean, forming the same time, what you calculate integral once and just form,
yes.
Yeah. So, as much as you can.
Exactly. So I mean, there are various ways to speed up the computation of ingredients of the REKS method. So for example, REKS Fock matrix and REKS energy. We didn't try all of them, to be honest, but I think that it can be made say fast enough, this methodology. And in practical terms, I don't think that you may have to go far beyond, for example, 4 or 6 active space, because these will apply mostly to some kind of molecules with degenerate orbitals, where you need indeed to guarantee that all degenerate orbitals are properly included into the active space.
Unless you break many bonds at the same time.
Yeah,
that's not what we usually do. If you break one bond at a time, you don't need that much of So unless you break the nitrogen N2 molecule, that requires 6,6.
Yeah, that would be 6,6.
But we don't usually do it.